Okay, good morning, everyone. I hope you all are doing well. I'll be back soon, don't worry. And I want to talk today about parametric equations. If you hear something yelling in the background, that is just my cat that thinks he's a dog and really needs a lot of extra attention. So do the best you can to ignore it. I apologize. So today we're going to be talking a little bit about parametric equations and how they relate to motion. So we just finished talking about vectors and what are parametrics used for? So first off, what is a parametric curve? So it says a parametric curve. It's used in many real world applications. We'll see the next time I do another video, or the next time I'm in, we're going to talk about projectile motion in relation to parametric equations. But in the meantime, they also use it for like 3D printing and machinery, mechanics, things like that, on Ferris wheels, so rectilinear motion. So things like that, we can see that we use parametrics for. So what is a parametric? So parametrics, so it says, is often very helpful in many real-world applications to write functions as a common parameter. In parametrics, we write all functions in terms of a common parameter t. T is typically referred to as time. So it says where each component, x and y, can be expressed as a function of time. So we could write x of t, y of t, or we could just say x equals f of t, y equals g of t. And it sounds really complicated, but they're actually not terrible compared to what we've seen before. And it makes sense when you think about it. Now, the one thing that I will specify as we're going through this, and I know a lot of you are probably going to think it, so let me clear it up from the beginning, and it is time. So if t is time, how can time be negative, right? Isn't it always positive? Well, we're also representing different functions x and y in terms of time. So in order to represent the entire function, sometimes we need to have time as negative. In the real world, no, we don't consider time to be negative, though, in theory, time travel can go backwards, but not going to go there. So yes, when we're creating a graph of a function, you will sometimes see time as negative. But when we get to projectile motion, we know that time is only going to be positive or 0. Okay, so we're just going to start out very simply, and we are going to graph the curve defined by the parametric equation. So now when you graph a curve defined by a parametric, rather than having a normal table where you only have two variables, x and y, or whatever they are, you're going to have t, you're going to have x, and you're going to have y. Because what you have now are essentially two equations that you're going to plug into. So now t tells you what you're going to plug in, so everything between -2, since it's equal to, and 2. Okay, and so I'm going to plug in t for x, and if I plug in t for x, I'm going to get 12. If I plug in -1, I get 3, 0, 3, and 12. So I plugged it in for this function for x, and then y equals 2t, so I'm going to plug in 2 times t. So t is -2, so it's going to be -4, -2, 0, 2, and 4. Okay, now what did I have here? Why did I leave this extra space? So technically, the point that you are graphing is the point x comma y. So you're not really graphing t itself. You're graphing it indirectly because both of these are a function of t. So the point you're really graphing is 12, -4, 3, -2, 0, 0, 3, 2, and 12, 4. Okay, so you're not directly graphing t at all. So if we go to graph this, and this grid is a little bit wonky, I'm just kind of going to change it a little bit. Say, hey, that's 0, 0, and we're just going to approximate it. So we'll go out to 12. So I'll make this down here -4, -2, 2, and 4. And I'll just make 12 out here. So if we go out to 12, -4, 3, -2, 3 would be somewhere around here. So if we're going 3, -2, 0, 0, 3, 2, so I'll be up here instead. And then we'll be out at 12, so positive 12. Okay, now keep in mind, because we have t on a limited parameter. So for example, t is only between -2 and 2. So we can't extend our function. So we can't put arrows there. It is stopping at these endpoints. Okay, it's not extending in all directions. Sometimes when you see a parametric curve graphed, because it often represents some sort of motion, you'll see arrows on it. So what do I mean? So from going towards -2 to 2, so you'll see almost like arrows. You'll see it's like representing a particle moving. Maybe some of you have seen this in physics and whatnot, getting from one point to another. Okay. So now looking at the next example again, you're going to do t, x, y, and then your points x comma y, and you're going to plug in your t values. You can start seeing, like, you don't have to plug in like -3, 3 for the next example. I'll just fill this one in. But you don't have to plug in every single t value. Definitely plug in the endpoints as always. Plug in a few points in between. So maybe you want to pick for this one -3, 3, 0, and 1. Some points in between. But you don't need to pick every single point. Make sure you pick the endpoints. Make sure you pick a few points in between. But you don't need to plug in 6 or 7. Okay, 4 or 5 is fine. So if we plug in for x here, we're going to get -2. If we plug in 1, we're going to get -1. Plug in 2, we're going to get 2, 7, and 14. And then if we plug in for y, we're going to get 0, 3, 6, 9, and 12. And again, we can plot our points. -2, 0, -1, 3, 2, 6, 7, 9, and 14, 12. And we can go and we can graph this. And I believe I'm just going to graph it on here. I'll make this -2 out here, so -2, 0. That's where I'm starting. -1, 3. So I'll make that 1, 2. I guess I'll do it a little bit more spaced out. So -1 up 3. So there's that. 1, 2, 6. So 2, 1, 2, 3, 4, 5, 6. 7, 9. So we increase a lot there. So it's 2, 4, 6, 7. And then move up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 14, 12. So it's going to be way up here. Just approximate it. I apologize, the grids I gave you are not that great. And again, we have our motion typically going for parametric, going towards that final point. If you want to pick even more points in between, you can. You're creating a table in the first part of these notes. Okay, so what I'm going to do is I'm going to pause this. I'm going to fill in the next table, give you a second to look at it, and then we're going to move on. Okay, so keep in mind, I just filled in example 3. Again, I did not pick every point in between, but I picked a good amount of points. Something to think about when it comes to graphing parametric is that I'm picking a certain range for t. Okay, a certain few different values. So the more values I pick, the more of the curve that you're going to see. So if I keep going -4 to 4, -5 to 5, depending obviously on what the curve is, you may see more points. So this is how to just plot a parametric using a table with t, x, and y in it. Remember, you're not actually plotting t itself. You're plotting the point x, y, that is, each of those variables are in terms of t. So let's go on to the next page and see what we're dealing with here. Okay, so what I want to show you is how to use the graphing utility on your graphing calculator to graph a parametric. So just like I'm going to Polar, so I'm going to pull up the graphing calculator, and you want to go to mode. Okay, now if you go to mode, it doesn't really matter if you're right now in terms of degrees or in terms of radians, but what does matter is that you go down, and a lot of you are probably back in a function. Remember, this is where we had our Polar button, but you want to scroll over from function to parametric, hit enter, and then you can clear it out, okay? You can clear it out, whatever it says. So now what I want you to do, when I give you these parameters in your notes, I say to graph the following parametric curve using graphing utility with an x-min, so we're going to go into our window, okay? And your t-min and t-max is going to depend on the problem. I believe for the first one, I tell you that t is between -4 and 4, so that's what you're going to fill in there. So that's where I put the -4 and 4. So you're going to put that in. Your t-step you can leave as 0.1, that's fine, I tell you that in the problem. In the direction for the problem, I tell you to set your x-min to 0, your x-max to 15, your y, you can keep your scale at 1, your y-min to -5, and then your y-max to 5. And you can keep your scale at 1 again. Okay, and then you want to go over to y equals. Now what you'll see is you'll see that when you're in terms of parametric, you're now not just going to have y equals, but you're going to have x sub 1, and you notice it says t there, so that means the variable's t, so x of t and y of t. So we're going to plug in our first equation. Our first equation is x equals 3t squared over 4, and y equals t. So that's what we're going to do. X equals 3t squared over 4, so you can put it in. Remember, so let me just show putting this in. So we're going to put in the 3. You're going to go to the variable. You're going to put in the square button. Let me clear it out so it doesn't give me an issue. So 3t squared. You could just do divided by 4. Hit enter, it's going to take you down to y. Now in this case, our equation for y is just y equals t. We already set our window to everything we wanted. T was -4 to 4. And now all we have to do is hit graph and your function will come up. Okay, your parametric equation in this case. So you'll see if you plot it, this is exactly what it will look like. I believe we already, no, we didn't look at this one in notes, but I'll show you in a little bit how to get it in terms of one variable, and you'll be able to show what the figure is. Okay, so the next one on here, if we go to plot that one, I'll do this one really quick too. So it says 3t squared plus 12t plus 12 try that again. 3t squared plus 12t plus 12. Hit enter. And then we're going to put in y. So y is 2t plus 4. Our window in this case, our t is between -4 to 0. So I'm just going to change my t max to 0. I'm not going to change anything else. And I'm going to hit graph. Okay, sorry, there's a little glitch in the system. So yeah, and this is what the function will look like. And of course I told you, I know the problem doesn't say this, but you can always play around with the different values for t. So say you change it, I don't know, from 0 to 4 instead, see how it affects the curve. And you're only getting a little part of the curve. So maybe you want to see, okay, so it said -4, maybe I'll put this one from -4 to 4 and see what I get instead. I also found a cool website, Open Omnia, which has, particularly for this, I can't speak for anything else on here, you all might know better, but you're able to plug in and graph the equation, and you can adjust the t value for the curve in the exact same way. So if you want to play around with that, that is up to you. Okay, but that's just a little bit on using the TI-34. Again, make sure you change the mode, make sure it's not in function, that's just normal, or polar, make sure it's in parametric, and do not forget to adjust your window to whatever the problem tells you. Typically, you can leave, once you change your x-min, x-max, y-min, y-max, generally you can leave them for now, and you can just change the t-min and t-max and play around with that, okay? And of course, you can go in and sketch the curves if you want to towards the problems. I pulled them up on the TI-84. Practice pulling them up yourselves, even if you don't have your graphing calculator in school, that's okay. Just play around with it, know how to use it. It's nothing crazy, just making sure you're in the correct mode. So going forward from here, the last thing we're really going to focus on today is finding a rectangular equation for a parametric curve and also like identifying the curve. Kind of like what we did when we were in polar, where we said, okay, convert it to rectangular, convert it to polar, and then identify what the curve is. Is it a parabola? Is it a circle? What is it? So we're going to do the same thing here. A lot of times you'll hear this referred to as eliminating the parameter. So what are you eliminating? Well, indirectly, you're eliminating the parameter t, and you're just getting your function in terms of x and y. So looking at the first one, it's always easier when both of them are linear. So we're going to look at x and y here, and we're kind of going to ignore this where t is from negative infinity to infinity. We're just going to focus on getting rid. So in y here, it's like solving a system. So we're going to figure out how to replace the t with either x or y in one of the equations and isolate and solve for y if we can. So in this case, we have that y is equal to t. So the easiest way is to look at x equals 1 plus t, and I'm going to, since y and t are equal, I'm going to replace t with y. And I'm going to solve for y. I'm going to subtract 1 over, so y equals x minus 1. So this is a rectangular form of both of these parametric curves. So if I were to make a table, just like we did before with t, x, and y, it would end up looking just like the line y equals x minus 1. So this function is linear. So get it in terms of y and x, and then identify what it is. And obviously we can go and graph that curve. If you don't believe me, do it yourself, plug in your graphing calculator and check it. You can always do that. The next one, so it's a little bit more challenging when, like I said, both of the functions are not linear. So looking at these, which one is it easier to isolate? So it's a lot easier to isolate t and get t in terms of y. So t would equal y over 2. Why would I want to do that? Why would I want to get t alone? Well, I want to get t alone because I want to replace t with something in terms of x and y. So in x equals 3t squared, I'm going to replace the variable t with y over 2. Make sure it's in parentheses. Okay, and now I'm going to solve this a little bit. I'm going to distribute the squared. Okay. And I really don't like leaving it in terms of x if I can help it. So yes, this is technically in terms of x and y, but let's try to get y alone. A little bit of manipulation here. So I'll get 4x equals 3y squared. Divide by 3. So y squared is equal to 4x over 3. Take square root of both sides. Don't forget your plus and minus. Okay, and yeah, I guess you can bring the 2 out in front, but y, it's not going to make it too much better anyway, so you might as well just leave it under there. If you want to take it out. Okay, just leave this like this. Now, if we were to identify it, what would this equation of this curve look like? So this is just going to end up being a sideways parabola. Anytime that you have, again, you can plot this, you have x equals y squared, it's the opposite, it's going to be a sideways parabola. You can go from there. But the whole point is, just like we did in these past 2 problems, you want to essentially get t alone in terms of one of the other variables so that you can replace t, with either x or y. It's always easier, usually, if you can, plug in something in terms of x for t and y, but that's not always possible. Here, it's just easier to get t equals y over 2 and then plug in on the other side. Go with what's easier. Okay, so what I'm going to do is I'm going to solve out this example, and I may actually solve out the next example in the exact 2 ways, and then you can check yourself on them. Okay, for this next one, so what I chose to do, and you could have instead gotten y alone and plugged in for x, I just said, okay, let me get, in this case, I'll solve for t in this equation, so I'll get t alone. So I got t equals x minus 1 over negative 2. And then in my other equation, what am I going to do? Well, just like a system, I'm going to replace t with x minus 1 over negative 2. Why? Because I want to get rid of t and have it in terms of x. So my only variables would then be x and y. So I'm going to replace t with x minus 1 over negative 2. It was a lot easier to just split this up and just have negative 1/2 x minus minus becomes a plus 1/2. And then I distribute the negative after. So I get 2 minus negative 1/2 x, which becomes plus 1/2 x, and then minus 1/2, and then I just simplify. Y equals 1/2 x plus 3/2. And take your time. The concept is not hard. You just want to get t alone and replace it in the other equation that you did not use yet, so that you only have an equation in terms of x and y. It's just the algebra, just like anything else. It gets a little harder. And this is linear. It's just y equals mx plus b. Okay, and then looking at this next one, again, so it's a lot harder to get t in terms of x. In this case, because you're taking the square root, you get a plus or minus. So start with this equation on the right. Start with the linear equation. Get t alone. So t equals, move the 1 over, y minus 1. And then we are going to replace, in our first equation, we're going to replace the t in the t squared with y minus 1. So it's exactly what I do. I just take it and I plug in y minus 1, so I get x equals y minus 1 squared. Take the square root of both sides. Don't forget that you'll get two answers, plus or minus. Square root of x equals y minus 1, and then get y alone. Add 1 to the other side. So again, what is this? Anytime you have x equals y squared, it is a sideways parabola. So you are seeing a lot of the same functions. Okay? And you will find if you Google eliminating the parameter, if you want more examples, you could also check in the online textbook I always give you. But if you want to look up eliminating the parameter, parametrics, you will get a lot more examples as well. Okay, so the last one we're going to talk about is kind of using identities. So using identities to help you a little bit in this case. So you want to eliminate your parameter t. So there's a little identity we talked about. So we want to find a way to connect x squared, y squared, t, and that whole lovely game. So a little reminder, we talked about an equation where we said that sine squared plus cosine squared was equal to 1. And it was some theta, some angle, right? That was our main Pythagorean identity that we talked about. So we want an equation. We know that x equals a cosine of t and y equals a sine of t. Okay, so rather than dividing and there's no way to really divide out by t here or taking the inverse, anything crazy like that, let's apply this identity. So what do I mean? So I know that, let's think about it this way. If I were to get cosine of t alone, so if I divide both sides by a, I would get x over a equals cosine of t. If I do the same thing over here with y, I get y over a equals sine of t. And we said that the variable itself, when we do trig equations, trig identities, didn't really matter. So let's keep that in mind. So think about this. The identity can be true as long as it's squared. So cosine squared t, we know plus sine squared t is equal to 1. Well, cosine of t is equal to x over a. So x over a squared, we can actually replace cosine of t with x over a, just don't forget to square it, plus, what is sine of t? Well, sine of t is y over a. Just don't forget to square it. We know that it has to equal 1. Let's clean this up a little bit. So I'm distributing the squared. So I'm going to get x squared over a squared plus y squared over a squared equals 1. And then a nice way to get rid of the denominator here is just multiply every term by a squared. So if I multiply everything by a squared, that goes away. The a squared in the bottom under the y squared goes away. So I just get x squared plus y squared equals a squared times 1 is a squared. So what is this the equation of? Think back to polar. This is just x squared plus y squared equals a number squared. It's just the equation of a circle with the center at 0, 0 in this case, and a radius equal to A, whatever A is. And I'm going to not go through this last one. We'll talk about it a little bit and how this can matter when I get back. So don't worry about that too much. Okay, and remember, pause the video throughout. If you have any questions, email me, and I will do my best to get back to you, send you a remind, anything like that. And the last one for today that we're going to talk about is find parametric equations for a curve defined by a rectangular equation. So looking at this, it says find parametric equations for a curve defined by a rectangular equation. So I'm giving you y equals x squared minus 4. We know f of x, same thing as y. And I am telling you to write it in terms, so write x and y in terms of t. So what's the easiest way to do this? The easiest way to do this is define x just in terms of t very simply. So our first equation would just be x equals t. Okay? So if x is equal to t, it's almost like working backwards to what we did before. What does that mean y would equal? Well, you can replace x with t. So that means that y would equal t squared minus 4. This is the most basic equation. It's a set of parametric equations that are in terms of t. So x and y are in terms of t. But if you were to go backwards and eliminate the parameter, you would get y equals x squared minus 4. So one thing you can always do, usually, 99% of the time, is take the simplest variable, in this case x, set it equal to your parameter t, and then that would make my equation very nice. Okay, and you can see this example in that Sullivan PDF as well. So again, that's all I'm going to give you for today. I believe I have this assigned for Wednesday. I'm recording this on Tuesday, so what I want you to do is, I know it's a pretty long video, is go back, watch it. I'm not going to actually give you an assignment to do today besides filling in the notes. Okay, so fill in the notes, go through them, do the best you can. If you have any questions, email me. Look up other examples of eliminating the parameter if you have to, but this is your work for today. Filling in these notes, seeing if you have any questions. I know it's like a half-hour video. Take the other half hour of class, going back through it, pausing it, looking at it. And like I said, please let me know if you have any questions at all. I'll most likely be posting an assignment for tomorrow, so for Thursday, and then I may or may not be posting new notes, probably a little bit about projectile motion on Friday, and I should be back the following week for you, okay? I can't wait to see you all. I do not have your test graded. I know you want to ask. I don't have them here, but when I get back, I'll have them graded, answer all of your questions. I hope you have a fantastic day, and again, can't stress enough, email me if you have any questions. Have a great day, everyone.